Hey folks, in Lesson 18 we're going to continue to develop this work-energy relationship into more useful terms that we can use. And eventually at the end of this lesson we'll be at the total energy of the system and be able to use this and apply this to solve for the dynamics of the system. So recall what we did is we started out by learning how to calculate the work done on a particle. And then we've transformed that into a relationship that we call the work-energy relationship that tells us the relationship between kinetic energy and work. And there are really three situations where this work-energy relationship is helpful. So the first is where all the forces on the particle equal to zero. And what this is telling us is simply a conservation law. And so it's where the kinetic energy is conserved in this work-energy relationship. The next is where we actually know the force for every time point, or if that force is constant. And so if we know this information, we can solve that integral more easily. And so this is what we've done so far in the more complicated problems, is that we've known the force. It's typically been gravity or a friction force, and we're able to use that information to solve for the problem. And the last case that we're going to focus on today is when the work done on a particle is independent of the path of the particle. And this is important because the integral itself is along the path. And it's along the path through this incremental path dr. And so if we can divorce the actual path of the particle from its ability to do work or from its quantity of work, then that really almost negates this integral and makes it really easy to calculate. And so this is called, when this occurs, this is called a conservative force. So a conservative force is simply defined as the force in which the work done on the particle depends only on the starting and ending points. It has nothing to do with the actual path taken. And so in our notation, we say that the work done on particle P by the force along the path alpha is equal to the work done by that same force along the path beta, which would be a completely different path, or any other path, and we can call those paths exactly what we want. And another important part of this is that if our path is closed, so essentially saying that if our path starts at some point O, and we can move along a path, but we end back at the point O, then that means that no work is done on the particle. So that's what this integral definition here says, in which this is a path integral with a closed loop, and then we have our normal integral, is that if you end up back at the same spot, then if the force that's doing the work that we're considering here is conservative, then the work that's done on the particle is equal to zero. Now we'll do a couple case studies later on in which we can use to better understand what a conservative force is and how it acts. But let's keep going and develop this idea into a more useful form. So if we have a conservative force, then we don't need to know anything about the path. Then calculating the work done by a conservative force is actually pretty easy. So let's define our work done by a conservative force on particle P as W sub P, and then the superscript is going to be a C for conservative force. Now this is going to be the work from time 1 to time 2, and this will be equal to the integral, and now we don't need to integrate along the entire path, it's only from position to position. So we get a definite integral where we go R of P with respect to O at time 1, and we integrate that R, P with respect to O at time 2. So those are our beginning point and our ending point. And then this is going to be of the integral, so it's going to be our conservative force dotted with our differential position as observed in the inertial reference frame. And because we have a definite integral now, we can simply take the integral and then evaluate the integral at these 2 points. So it'll be the integral of our conservative force F sub P dotted with dr P with respect to O as observed in the inertial reference frame. So we'll calculate that integral, and then we'll simply insert R of P with respect to O at time 2, and then we'll subtract from that the integral Fp dot dr P with respect to O as observed in the inertial reference frame, and evaluate this at our position at time 1. So we've now parsed out the work that's done only by conservative forces. If this is the conservative force, that we can calculate a definite integral, evaluate it at its final time, or the time 2, and subtract the evaluation at its initial time. And our units are in joules. And so our units are in joules. This is energy, using the work-energy relationship. So let's take this and let's define a new parameter that is actually in terms of energy. So that term we call potential energy. And potential energy is a scalar, and we're saying that it's the potential energy of point P with respect to O. We write this the same way as we write the kinetic energy, and this is due to Fp, and if we're using potential energy, this Fp has to be a conservative force. So it's this conservative force, and it's on the particle P, so it's moving along this position vector r P with respect to O. And then we define this as the negative work that's done. So negative integral of this conservative force dotted with the differential position. Now one thing that might look a little bit strange here is that there's a negative sign in front of the integral. So we're actually defining the potential energy as the negative work. And so this is simply a convenience that's going to make the calculations much easier later. So bear with me on this as we insert this into our work energy, or our work done by conservative forces, and then you'll see how these signs work out at the end when we get total energy. So here's our expression from before, and then let's insert into this the potential energy at time 1 and time 2. And so our first term, evaluated at time 2, we get the potential energy there is going to be the negative potential energy because we have a negative sign in front of it. It's U, P with respect to O. This is due to these conservative forces, and this is evaluated at time 2. And then we get a minus our work at time 1, or minus the potential energy at time 1. So when we insert this, it's plus U of P with respect to O. This is due to the conservative forces, Fp, and this is evaluated at time 1. Now what we're going to do moving forward is, because potential energy we can only use potential energy when we have conservative forces, we're going to drop this term, these superscripts, because they really are superfluous in this case. So as we move on, we're going to drop the superscripts on our potential energy and just move through the derivation. So now, recall that we have a work-energy relationship. And the work-energy relationship simply states that the kinetic energy at time 2 is equal to the kinetic energy at time 1 plus the work that's done, and this is the total work, so this is the work that's done by all forces on the particle P traveling along the path gamma. We've now taken this one step further, and we've taken the work that's done by all the forces and separated this into two different camps. We've got the work done by conservative forces, and then we've got the work done by non-conservative forces. So we can write our work-energy relationship in an expanded form, where we say that we have our kinetic energy at time 2 is equal to the kinetic energy at time 1 plus the work done by conservative forces from time 1 to time 2. Oops, let's keep the notation that we're using. So the work done by conservative forces along that path plus the work done by non-conservative forces along that path as well. So now if we substitute our relationship here between potential energy and our work due to conservative forces, substitute this into our now expanded work energy relationship, we're going to get the following, where we have the kinetic energy at time 2 is equal to the kinetic energy, P with respect to O, at time 1, and this is plus the potential energy of that particle with respect to O at time 1 minus the potential energy, P with respect to O, at time 2, and then that took care of our conservative forces. Now for our non-conservative forces, we don't have any shortcuts for it, so it's simply the work due to non-conservative forces along the path gamma. And so now with this relationship, we now have an expression for the total energy of the system and how that energy changes from time 1 to time 2 along the path gamma. And so we can simply move some terms around and put the energy at time 2 on the left-hand side, both our kinetic energy and our potential energy. And the energy at time 1, those should be 1s, energy at time 1, both our kinetic energy plus our potential energy at time 1 on the right-hand side. And then the difference between these two, what's making the energy change, is going to be the work due to this non-conservative force. And so what we have here is this is the energy of P with respect to O at time 2. It's equal to the energy of P with respect to O at time 1, and then plus our work due to non-conservative forces along the path that it takes, because if it's a non-conservative force, it does depend on the path. And then what we have here is that this term on the right-hand side, this is going to be energy loss. So our energy at time 1 is always going to be higher than our energy at time 2, because this energy loss is going to decrease the energy of the system that's going to dissipate into heat or some other form. But if there is no non-conservative force working on the system or performing work on the system from time 1 to time 2, then we can still have movement. In fact, we can have a lot of movement, but energy is now conserved in the system. Alright, let's get a better handle on this idea of conservative forces and how this fits in with potential energy by dealing with local gravity. It's something that we're familiar with, and with local gravity, we're saying that the potential energy of gravity is equal to mgh. And so we know this. I'm sure that you know this because your high school physics teachers told you this, because your university physics teachers told you this. But let's actually figure out why that's the case. So let's take a mass and let's put it into gravity. Let's only have gravity acting on it. And let's take it from path A, or point A, to point B. And if this is a conservative force, then it shouldn't matter what path we take from A to B, but we're still going to have the same amount of work that's done on the particle. So let's say that there's a height involved here. We'll just call that h. And we need to put our reference frames on. And so here we see an inertial reference frame with the basis vectors of E1, E2, and E3 defined how we normally would. So first let's get a better handle on the fact that gravity is a conservative force. So if we're going to start at point A, and then we're going to drop our mass, and it's going to go to point B, then let's calculate the work due to gravity on that mass. We'll have the work on particle P due to gravity, so this is mg, and it's r, P with respect to O, along that path from A to B. And then this is going to be equal to the integral of our force, and so our force is going to be constant the entire way down. So regardless of where the particle is, as it's going down, we're always going to have a force acting on the particle of mg. And it's mg in the negative E2 direction. So we put in here negative mg in the E2 direction. We're going to dot this with our differential distance. So let's define our y going up. And so that means that this is going to be dy in the E2 direction. And then when we make this calculation, we're going to be going from a height of h to a height of 0. So our integral bounds are 0 to h, and so we'll get negative mgy evaluated from h to 0. Whoops, my bounds are incorrect here. We're going to go from h to 0. And so this is going to give us mgh. So mgh is the work that's done along the path from A to B if we just simply drop the mass and just let gravity do its thing. So let's do the same thing if we take our particle from A and then let's move it to the right and then drop it and then move it to the left to B. So this is a simple path. And as we move to the right, we still have the same force vectors that are acting on the point as it goes across. Now those force vectors are all going to be of a magnitude mg, and they're in the negative E2 direction. But they're not doing any work. Gravity's not doing any work at all because these forces are orthogonal to the path. And then when we drop it, we get those same forces that are on the particle in which it lands. And then as we move from this point to the left, we're going to get the same force vectors that are applied, but once again they're orthogonal to the path. So our work due to gravity along this first leg is 0. The work due to gravity along the second leg is going to be mgh. And then our work due to this last leg to finally make it to B is going to be 0. So we see that we changed our path, and even though we changed our path to move to the right, to go down, and then to the left, the work done on the mass itself to get from A to B is going to be mgh, which is the same as if we just simply dropped it. So now let's change the path a bit, and let's follow our point A to the right, which we've already established that if we move it horizontally it doesn't do any work. And then let's slide it down a ramp all the way from here down the ramp to point B. And let's calculate the work as we go from across and then down this ramp. The ramp has a length d, and then it's starting at the same height h because it's parallel with A. We need to apply a new reference frame, and this will be reference frame B, which is defined by the basis vectors B1, B2, and then B3. So we have an origin at B. And we have an angle theta that's relating the orientation of these two reference frames. And then we get our transformation table to help relate these two reference frames to each other. And we'll define our coordinate S that'll help us put this particle on a path down the ramp. Due to gravity, as it's sliding down this ramp, and the force due to gravity is always going to be mg in the negative E2 direction. And so this force, when we write this into our integral, will be negative mg in the E2 direction. And then our differential distance is going to be ds in the B1 direction. And we're going to be starting at d, a distance d away, and moving to 0. So our integral is d to 0. And then here's our force, and then there's our differential distance that we're going to integrate. Now, because we want to use this in terms of a path, we want to convert our basis where we have an E2 into the B frame. And so E2 is equal to sine theta B1 plus cosine theta B2. And so we'll insert this, which makes our integral from d to 0 of minus mg sine theta B1 minus mg cosine theta B2. And then we're dotting this with ds in the B1 direction. And so when we take our dot product, we get the integral from d to 0 of negative mg, and it's only the sine theta term, ds. And let's take our integral, which will get minus mg sine theta s evaluated from d to 0. And then this is equal to mg sine theta d. And we see from our picture here that d sine theta is simply equal to this leg of the triangle, which is conveniently h. And so the work due to gravity as this slides down the ramp, r p with respect to o, along this path zeta, is equal to 0 as we move from A to get to the ramp, and then from the distance d away as it slides down the ramp, it's equal to mgh. So this is going to be the same. This is going to occur no matter what in the presence of a conservative force. And so it doesn't matter in this case whether we decide to take a path that goes straight down, moves to the right, down a ramp, to the right, down, and to the left, or if we decide to take kind of a crazy path. It really doesn't matter. It's path independent, and the work is always going to be the same if the force is conservative. And if you'll recall the second part of that definition, it said that if we start at a particular place and then we take a path, and it doesn't matter what the path is, and we end up at the same place, then the work done on that particle is going to be equal to 0 because it's a closed path. And so in this case, you know based on experience that the potential energy at this point is going to be the same as the potential energy at that point, which is mgh, and it's mgh. So now we've established that that gravity, this local gravity, is a conservative force. And so let's take a look at this potential energy function, where we have the potential energy of P with respect to O, and this is of the force mg. And this is equal to the negative integral of negative mg in the E2 direction, and this is dotted with dy in the E2 direction. And so we get the expression just in this definite integral of mgy. And this term mgy is what we call a scalar potential function. So the value of your potential energy, and this, or the value of the energy here, is a function of y. So it depends on how far you are away from a reference line in this case, or a reference point. And in this case, it's a direction, or it's a direction that goes against gravity, y, and that's how far you are from that base point. And this is where the word potential energy comes from, because this is a scalar potential function. And so a scalar potential function is defined as, there are two requirements that this has to be for this to work out as potential energy. So the first requirement is that the negative gradient of potential energy of any force, or any conservative force rather, has to be equal to that force itself. So let's check our scalar potential function that we just developed for gravity. And so the gradient, so we're saying that the negative gradient of our potential energy for gravity is equal to the negative gradient of mgy. And you know from your multivariable calculus class that this gradient is equal to the partial with respect to x of mgy. Oh, so we're doing negative gradient. So negative partial with respect to x of mgy in the E1 direction minus the partial with respect to y of mgy. So we're simply just inserting our potential energy, and then minus the partial with respect to z of mgy in the E3 direction. And so when we take these partial differentiations, the partial with respect to x of this function is 0, the partial with respect to z of this function is 0, and then the partial with respect to y of this function is going to be negative mg in the E2 direction. So we see that indeed the negative gradient of our function mgy is equal to the force itself. So we've satisfied that condition for potential energy. And then the next condition is that the curl, and recall that a curl is the gradient crossed with the force itself, has to be equal to 0. And so we can write this as the gradient crossed with the negative gradient of our potential energy of that conservative force has to be equal to 0. And so when you have a curl, which is the gradient crossed with a force, or a force field in this case, if it's not equal to 0, then that indicates that the vector field itself is flowing in a circle, that it has curvature to it, and so that's what happens when the curl is not equal to 0. And so we know, simply because we've drawn this vector field multiple times, that gravity doesn't have a curl to it, and so as a result, or doesn't have a circular pattern to it, and so as a result, the curl of that vector field is going to be 0. So hopefully this has begun to answer some questions that you may have had about conservative forces and how this works out for a potential energy. We get the idea of a potential from this term, a scalar potential function, and then with these two requirements here, where we have the negative gradient has to be equal to the force itself, and then that the curl has to be 0, meaning that it's not circular. And so this is local gravity, and we have two other conditions that we use, or that we define specifically, and one of those is a spring and the potential energy of a spring, and then the other one is the potential energy of big gravity. Big gravity being Newtonian gravity, where you've got a small mass and a large mass, and recall that we also called that a central force. And so we can apply potential energy, or be on the lookout for these three conditions. These are all conservative forces: local gravity, a spring force, and then big gravity. All right, let's do an example. So here we have a collar that's sliding on this rod. It's 2 kilograms. It's constrained to move in the plane along this rod. This rod has friction. It's angled at 45 degrees. We're given a coefficient of friction, and we also have a force that's applied to it to the right, in the direction to the right. So what we're doing is that the collar starts from rest at A. We let this go, we apply the force, and then we want to find the collar's speed when we get to B. And so to work this problem, we're going to apply our energy balance. So it's going to be our total energy, which we've defined as our kinetic energy at time 2 plus our potential energy at time 2 is equal to the energy at time 1, which is our kinetic plus our potential, and then plus the work due to non-conservative forces. So as in anything, any dynamics problems, let's define our reference frames and coordinates. And so first we have an inertial reference frame that we have E1 to the right, E2 pointing down, E3 into the page, and we have an origin at A because that's where we're starting. And then we'll apply another reference frame, which is also an inertial reference frame, but reference frame B, which has an origin at A, and then we have B1 pointing down the rod, B2 orthogonal to this, and it's rotated from reference frame I by an angle of theta. And we have our transformation table here that relates these two reference frames with each other. The location of our mass, P, so RP with respect to A, is equal to, we have our coordinate defined as x, so it's x in the B1 direction. And at time 1, our position is 0, and at time 2, r p with respect to A is equal to L in the B1 direction. It's a good idea to draw your free body diagrams in these problems early instead of waiting till later. And the reason why is because we really don't have kinematics to deal with here. So for our free body diagram, let's draw all of our forces that are applied to this. We have a force to the right, which we'll just call F in the E1 direction. We have gravity, and that's mg in the E2 direction. We have a normal force, so we'll say N in the B2 direction. And then we need to apply a friction force. And so let's put friction along the positive direction. And so this friction force is negative mu in the B1 direction. And so with this information on our free body diagram, we can begin to identify which forces are conservative and which forces are non-conservative. So we've said that our conservative forces are going to be gravity, big gravity, and springs. And so that means that here we only have one conservative force, and that's going to be our local gravity, and the rest of these are going to be non-conservative. So let's write out our expression for our non-conservative force, because we know that we're going to have to calculate the work due to the non-conservative forces later. So this is going to be N in the B2 direction plus F in the E1 direction, and then minus mu in the B1 direction. Let's make our transformation so we can do everything in the B1, B2. So our non-conservative forces are going to be N in the B2 direction plus F cosine theta in the B1 direction minus F sine theta in the B2 direction, and then minus mu in the B1 direction. Alright, so now let's take a look at each of the components in our total energy equation, and let's deal with them individually. So we have our kinetic energy at time 1. So this is T, P with respect to A at time 1. This is going to be equal to 0 because we're starting from rest. So our kinetic energy at time 2 is equal to 1/2 m v of p with respect to a as observed in the inertial reference frame. We always use inertial velocities. This is at time 2, and it's that magnitude squared. And this is what we're solving for. So we can't simplify this anymore. So then let's look at our potential energy, p with respect to a, at time 1. And we only have one conservative force. This is going to be gravity. And we've defined this scalar potential as mg, and then we'll take r of p with respect to a, and this is at time 1, and then we're going to dot this with negative E2. And the reason why we're dotting this with negative E2 is because this is implicitly saying that we're using point A as our reference point, and then we know that we need mgy, y being the vertical distance above that. And so at this particular time, it's right at that particular point, and so we've said that r of p with respect to a at time 1 is equal to 0. And so this does simplify to mg and then times 0 in the b1 direction, dotted with negative E2. And so we get 0 out of this expression. But let's do the next one, which is the potential energy of p with respect to a at time 2. And so this is going to be mg, and then it's r of p with respect to a at time 2. We're going to dot this with negative E2, which is going to give us our distance above point A. And so this is equal to mg, and then it's L in the B1 direction, dotted with negative E2. So we transfer this, we get mgl. And then to dot B1 with E2, we're going to get a negative sign on whatever we get. But to do B1 dotted with E2, we go to our transformation table, and then we have B1 dotted with E2, which gives us a sine theta. So B1 dotted with E2 is sine theta. Those are simply dot products up there. And so we'll get our sine theta. Okay, it's dotted with a negative E2, so we stick a negative sign in front of this, and then we can make our calculations. And so we find that our potential energy at time 2 is equal to negative 27.75 joules, and that should make sense because if we're starting at point A, we're going to point B. If this is 0 potential energy, then this is going to be a negative potential energy because the only conservative force that we're concerned with here is gravity, and we know that it should be a negative. You're losing energy. So we only have one term left. We've taken care of our kinetic energy at time 2, potential energy at time 2, kinetic energy at time 1, and the potential energy at time 1. We only have left to calculate the work due to non-conservative forces along this path. So the work due to non-conservative forces on point P, this is P with respect to A, along that path that P is taking, so down that rod, is equal to, it's going to be the integral of all the non-conservative forces, dotted with dr P with respect to A, as observed in the inertial reference frame. And so dr of P with respect to A, observed in the inertial reference frame, is our differential dx, and that's pointed in the B1 direction because we've defined B1 as down the slope. It's in the direction of the path. And so we're simply substituting our non-conservative force that we've determined from our free body diagram into this integral, where we have the integral of n in the B2 direction plus f cosine theta in the B1 direction minus f sine theta in the B2 direction minus mu n in the B1 direction, dotted with dx in the B1 direction. We're going to solve this from 0 to L, which is our x-coordinate at time 1, or x-coordinate at A, and then our x-coordinate at time 2, or x-coordinate at B. And so let's take the dot product within the integral. We'll keep our integration bounds. And when we get this, we're going to get only the B terms, because we're dotting with B. That's our path. And so we get f cosine theta minus mu n ds. And this is where we still need to solve for n. And so to solve for n, our normal force, we're going to take the dot product in the B2 direction of all of our forces that are applied to the particle. So that's going to be n in the B2 direction plus mg in the E2 direction minus mu n in the B1 direction plus F in the E1 direction. Okay, so these are all of our forces on our particle, and we're going to take the dot product in the B2 direction of all the forces, and we're going to set that equal to 0. And all we're saying here by doing this is we're saying that the B2 component of all the forces has to add up to 0, because this can't move in this direction. It's not a degree of freedom, so we can set all those forces equal to 0. And so we take all the forces, we dot it with that particular direction, we set that equal to 0, and we come up with the expression of n plus mg cosine theta, because E2 dotted with B2 is cosine theta. B1 term drops out, minus f, and then sine theta, because E1 dotted with B2 is negative sine theta. You'll see that in your transformation table, that's equal to 0. And when we plug all this information in, this gives us that our normal force is equal to 3.26 newtons. So we have our expression here, we have our work. We're going to take the integral of our work now, and we get f cosine theta minus mu n, all multiplied times L after we take our integral. And then when we plug in each of the values, where we get 15 cosine 45 degrees minus 0.4 times 3.26, all multiplied by 2. This gives us 18.61 joules. So now let's insert each of these parts into our expression that we have. And we have our kinetic energy at time 2 is going to be 1/2 m Vp with respect to A as observed in the inertial reference frame squared. Then we're going to have our potential energy at time 2, which we calculated as negative 27.75 joules. Then this is equal to our potential energy at time 1, which we said is 0. Kinetic energy at time 1, which is 0 because we're starting from rest. Our potential energy at time 1, which is also 0 because we're starting from the point at which we're referencing. And then our work due to non-conservative forces, which is 18.61 joules. And so when we solve for our speed, then we get 6.77 meters per second. Alright, so as a recap, what we did to solve this problem is that we used our total energy, in which we have our kinetic energy at time 2, our potential energy at time 2, equal to our energy at time 1, our kinetic plus potential, and then the difference between those is the work due to non-conservative forces. So to make this happen, we need to consider all of our conservative forces within our expressions for potential energy. So we went through the calculations for this. We found a number value for each of these terms, and then we simply added them up. So what's nice about this is that because we're compartmentalizing, once again, into kinetic energy, potential energy, and work, we can go back and check each of those expressions to be sure what we're doing is correct, and it makes it a little bit easier to spot mistakes than as if we just kind of went at this with a bunch of scalars. So in summary, we've now expanded on this idea from day one of energy, and with energy, turning that from work and turning that work into kinetic energy, creating a relationship, and now developing another tool, which is this idea of using potential energy for a total energy balance. All right, that does it. I'll see you in class.